All right, so now we're going to look at what is called a Lie algebra, which, as we'll see later, is related to a Lie group. Okay. Okay, so a Lie algebra. Okay, is a linear space. Let's call that V. Okay, which is equipped with a Lie bracket. Okay, and this Lie bracket is the following. Okay, so usually denoted by square brackets. It's like with two slots. It's a map from V cross V to V, and it satisfies the following. Okay, so the first one is that it's skew symmetric. Okay, and what skew symmetry basically just means is that if you take the bracket of f and g, it's equal to negative the bracket of g and f. Right, and this has to be true for, of course, all f and g in the vector space V. Okay, the second one is bilinearity. Okay, so basically bilinearity just means that it's linear in each of the slots. Okay, so what that has to mean is that if you take the bracket of alpha f and g, right, that's equal to alpha, the bracket of f and g, and this also has to be equal to the bracket of f and alpha g. Okay, so that's one of the properties of linearity, right? And the other one is that if you take the bracket of f plus g with h, that's equal to the bracket of f and h plus the bracket of g and h, right? So these two conditions together, it's like means it's a linear in the first slot. You want it to be linear with respect to the second slot as well. So the bracket of f with g plus h has to distribute as well. So that's equal to the bracket of f and g plus the bracket with f and h. All right, and so these conditions have to be true for all f and g in the vector space V and all alpha in the rails. Okay, and then the third property is what is called Jacobi's identity. Okay. And what it basically means is that if you take the iterated Lie bracket of three things, so f, the bracket of f with the bracket of g and h, right, and then you cyclically permute this, which basically just means that you shift everything, okay, in a cyclic fashion. So you have the bracket of g with the bracket of h and f, right, plus the bracket of h with the bracket of f and g. Okay, so you have this cyclic permutation. It's like of the things in the slot. So if you take this combination, right, that turns out to be equal to 0. So this is what is called Jacobi's identity, and it's some kind of integrability condition, if you will. Okay, all right. So these are the properties. It's like you'd want a Lie algebra to satisfy, and if you recall, it's like when we talked about vector fields, right, particularly in the context of Hamiltonian mechanics, we introduced this idea of the Jacobi Lie bracket of vector fields. Okay, and so as the name implies or sort of suggests, it turns out that that Jacobi Lie bracket is a Lie bracket, and it basically using that Lie bracket, that Jacobi Lie bracket, endows the space of vector fields with a Lie algebra structure. Okay, so let me just stop here for now.